I would like to thank the organizers for the opportunity to speak at the Quantum Summer Symposium. Today, I'll talk about something very basic, surface codes. I introduced the initial idea some 25 years ago, and now I'm excited to see that the Google team has made it a reality. Of course, now it's a textbook topic, so it may be boring to the more prepared part of the audience. But I'll mention some less known things at the end of my talk. The simplest in the family of surface codes is the toric code. It's a code defined on an L by L lattice on a torus. These black boxes represent the qubits. There are two L squared physical qubits on the L by L lattice. The qubits reside on the edges. Now, the code is defined in terms of stabilizer operators. Stabilizer operators are specific products of Pauli operators. In particular, we have stabilizers A sub S associated with vertices and stabilizer B sub P associated with plaquettes. A sub S is the product of sigma X around the vertex, and B sub P is the product of sigma Z around the plaquette P. The qubits acted upon are indicated by color. Red color stands for sigma Z, and green color stands for sigma X. The actual code is defined in a very general way. It's just the definition of a stabilizer code. Vector C is a code vector if it's a joint eigenvector of all the stabilizer operators, with the eigenvalues all equal to 1. A sub S does nothing to C, and B sub P does nothing to C for all S and P. For this to make sense, the stabilizer operators must commute with each other. And we see in the picture that A sub S and B sub P act on disjoint sets of qubits, so they obviously commute. But what about this case? Now, they share some qubits, but there are exactly two qubits shared. A sub S includes sigma X, B sub P includes sigma Z. Sigma X and sigma Z commute up to sign. There are two minus signs that cancel each other. So in the end, the two stabilizers commute. We'll see later that the code space dimension is 4, therefore it encodes two logical qubits. Now, let's consider the detection of Pauli operators by a general stabilizer code. Any error can be decomposed into Pauli operators. An error can be represented as a sum of Pauli operators of this form. It's sigma X acting on some set of qubits Jx times sigma Z acting on some set of qubits Jz. Now, let a Pauli operator E act on a code vector C of some code defined by stabilizer operators S1 through SL. Stabilizer operators are Pauli operators. E is a Pauli operator. Two Pauli operators may commute or anti-commute. In this picture, S is of X type. It's the product of sigma X on the green qubits, and E is the product of sigma Z on the red qubits. There is one qubit in common, therefore the two stabilizers anti-commute. The commutation or anti-commutation is indicated by a syndrome bit, mu sub j. If it's 0, they commute. If it's 1, they anti-commute. If we collect all those bits for all the stabilizer operators, we get the binary vector that is called the syndrome of error E. The syndrome is a property of the error, but it gets imprinted on any code vector the error acts upon. If it acts upon vector C, the new vector psi is characterized by new eigenvalue conditions, and those conditions contain the syndrome. So the syndrome can be measured by measuring the stabilizer operators. We can classify Pauli errors like this. We can break all Pauli operators into 3 disjoint classes. If E is the product of stabilizer operators, it acts trivially on the code. It means that it does not only preserve the code space, but it actually preserves each individual code vector. So such an error does nothing, it's completely harmless. An error is detectable if the syndrome is non-zero. Such an operator does not preserve the code at all, it takes it to an orthogonal subspace. And finally, there is a third possibility, that the syndrome is zero, but the operator is not a product of stabilizer operators. In this case, the operator preserves the code, but not individual code vectors. In other words, it acts on the code non-trivially. It's a non-trivial logical operator. We want to apply such operators in the process of quantum computation. But if they happen spontaneously, it's bad. Such an operator becomes a logical error, and it may ruin our computation. Now, let's apply these concepts to the toric code. We can consider Z-type errors and X-type errors separately. Let's focus on Z errors. An error is just a set of qubits, and qubits belong to edges of the lattice. Therefore, we may picture an error as a line or set of lines on the lattice. In other words, it's a Z2 chain on the lattice graph. Z2 chain can be of different types. The trivial type is when it is a boundary of a two-dimensional chain or a two-dimensional region, which means it's a product of stabilizer operators. The error is a product of stabilizer operators if it is a boundary, in this case, of this cyan region. An error is detectable if the one chain has a non-zero zero-dimensional boundary. In this case, there are 4 qubits affected, and they are drawn as 4 edges, and this set of edges has 4 boundary points, A, B, C, and D, and the stabilizer operators at those points, the X stabilizers, are unhappy. It shows in the minus sign in the eigenvalue equation. Those locations can be detected by measuring the stabilizers. And finally, a non-trivial logical error is a line going around the torus like this, from the left to the right. But this point and that point are actually the same point on the torus. So the line is closed. It's a closed line or closed one-dimensional Z2 chain, but it's not a boundary of any 2 chain. It's not a boundary of any set of plaquettes. And such an error is non-trivial. This slide shows an intermediate summary. The stabilizer operators are products of sigma x around a vertex and sigma z around a plaquette. They commute. And the errors can be broken into 3 classes according to columns, but the rows show Z-type errors and X-type errors. Z errors and X errors are very similar. In each case, an error is just a set of qubits, but for Z errors, it's convenient to represent them as edges of the lattice graph. For X errors, it's convenient to draw them as edges of the dual lattice, so they cross the original lattice. this dashed green line crosses the edges of the original lattice. A detectable error shows as boundary points those red dots or green dots, and let me call the red dots Z-type errors corresponding to X-type syndrome charges. Let me call them charges, and the other type of syndrome bits are called vortices. They're associated with the group Z2 and are somewhat analogous to electric charges and magnetic vortices in electrodynamics, which are associated with the group U1. To complete the description of the code, let's discuss logical operators and code distance. Logical parallel operators are defined as operators that commute with all stabilizers. Up to trivial operators, they form a group with generators Z1, Z2, X1, X2. This is specific to the toric code. Z1 is the product of sigma Z along a vertical line, and X1 is the product of sigma X along a horizontal line. And these two sets of qubits have one qubit in common. Therefore, Z1 and X1 anti-commute. This commutation relation is similar to the commutation of sigma Z and sigma X acting on a spin or a qubit. And so we may say that X1 and Z1 are logical sigma X and logical sigma Z acting on a logical qubit. Since there are two pairs of such operators, there are two logical qubits. The distance of the code is the minimum size of an untrivial logical operator. A logical operator is a line going around the torus, and the smallest length is L if the line is straight. It can wiggle, then the length will be greater. So the code distance is L, the size of the torus. The toric code can also be realized as a Hamiltonian, where we have stabilizer operators as terms and qubits as spins on a lattice, and count vectors are associated with ground states. So quantum information is encoded in the ground subspace of this Hamiltonian. However, this realization is different from the toric code I described previously. It differs in one practical aspect. The Hamiltonian realization does not correct errors per se. It rather avoids errors. If we keep the environment cold, if we keep the system cold, then the errors will not happen. This can work in practice, at least in principle. It hasn't been realized in practice yet. So let me describe active error correction, which is done by the Google device. We should correct all possible errors, including Z errors and X errors. Let me focus on Z errors again. X-type errors are similar. An error affects a set of qubits. These red squares represent the affected qubits. We draw them as a set of edges, but in fact, errors are invisible. What we can see and measure is the syndrome. The syndrome is a set of locations, those red dots, and we call them charges. Now, the device measures the syndrome and sends the data to a classical computer, and the computer's job is to infer the error. We infer the error by connecting the charges by lines. Here we connected them somehow. We connected these two dots going around the torus, and this is correct. This is exactly what the error was. But we didn't correct exactly in the same way these two charges. The error goes like this, and our inferred error goes like that. That's okay. If we superimpose the two pictures, we'll get a square, which is a trivial. And so, at the next step, we applied the inferred error operator to cancel the actual error. It doesn't cancel exactly, but it's fine. The product of the error operator and the inferred error operator is a trivial operator. It's just this plaquette. The cancellation is almost complete. We don't care about such operators because they don't do anything to code vectors. However, wrong inference results in a logical error. If we connect these two dots by a straight line rather than going around the torus, the difference between the actual and inferred errors is a line going around the torus, and that is a logical error. Now, the most interesting part in the previous story is the error inference algorithm. There are several algorithms that do that. Some of them are approximate, like the minimum weight matching. The minimum weight matching means connecting charges in pairs such that the resulting graph has minimum weight, minimum number of edges. We want to minimize the number of red edges, the amount of red in the picture. But that is only an approximation. The optimal algorithm is called maximum likelihood decoding. To describe it, we need to break individual errors or error patterns into topological classes. For example, these two errors are in the same class because if we superimpose the two pictures, we'll get the boundary of a rectangle. It is a rectangle going like this. And a rectangle consists of plaquettes, so it's a trivial error. And the two patterns are in the same class. This pattern is in a different class. If we superimpose the picture on the left and the picture on the right, we'll get a line that runs from the left to the right around the torus. And this line is a logical operator Z1. But on the torus, unlike the planar geometry I will describe later, on the torus there are more possibilities. A logical operator can go vertically. This superposition of this picture and that picture corresponds to a vertical line, and here the line goes diagonally. Now, if the probability of each individual error is known, we can compute the total probability of all errors in each class. We just add up exponentially many numbers. It can be done by brute force. It can be done in a smarter way. There are smarter way to decode, in particular for planar graphs. Then we select the most likely class, the class that has the greatest overall probability. That's called maximum likelihood decoding. This algorithm satisfies a threshold theorem. If each qubit undergoes a Z error and an X error with probabilities less than some threshold, which is about 11%, then the maximum likelihood decoding is asymptotically efficient. It means that if we construct an L by L code, the probability of a logical error in such a code scales down exponentially with the code size. As L goes to infinity, the probability goes down to zero exponentially, with some parameter alpha that depends on how close we are to this threshold. If we are at the threshold, then alpha is zero. If we are much below this threshold, then alpha is sufficiently large. The Google paper uses a related parameter lambda. It's basically e to the minus 2 alpha. Now, there are two caveats. Faster but less accurate algorithms, like the minimum weight matching, have a slightly lower threshold. In reality, there are also measurement errors, meaning that the syndrome may be recorded incorrectly. Those errors further decrease the threshold, and they require 3D error tracking in space-time. Google does that. The paper shows a picture describing 3D error tracking. And finally, each measurement is realized as a sequence of unitary gates. Any imperfections in the implementation of measurements produce multi-qubit errors. Thus, the raw per gate threshold is much lower. I mean, we don't count the probability for qubit to flip. If we leave the qubits unattended, they can flip spontaneously. It's bad. But when we correct the errors, we may introduce new errors. And we really care about the error rate in the gates that perform the measurement. And the threshold for errors in the gates is not 11%, it's much smaller. But there are some good news. Errors need not be fixed. They can be tracked in software. The decoding can be postponed until a decision point. A decision point is a point in a measurement-based computation, I'll touch upon that later, where we measure something and then decide what gate to apply next. At this point, the decoding must be complete. However, we're not computing yet, so we can take our time. We can first do the experiment and decode later. When we will be actually computing, we need to hurry up, but still it's not necessary to correct every error, to decode every error correction cycle. The decoding is tied to decision points in the algorithm. Now, surface codes are easier to implement if they are planar. The simplest planar code, as opposed to the toric code, is defined on a square. This is a schematic drawing. There are two boundaries. The bottom and the top are smooth, and the sides are rough. A smooth boundary can absorb vortices. We can run a vortex and produce a logical sigma x, and rough boundaries absorb charges. We can run a charge from the left to the right and produce a logical sigma z. These are the logical operators. There are also stabilizer operators in the picture. The bulk stabilizer operators are products of 4 qubits, and there are new boundary stabilizer operators that are products of 3 qubits. These are incomplete plaquettes and incomplete vortex stars. In the paper, you'll see a different graphic representation. Let me explain it. It's very simple, although the picture looks completely different. The qubits are represented by boxes, by squares. And stabilizer operators are just sets of qubits. In the left picture, we mark them using blue lines, drawing the lines along the edges of the original graph. But that is not necessary. The picture in the middle is simpler. We just connect those red boxes corresponding to sigma x and green boxes corresponding to sigma z, and green boxes corresponding to sigma x by lines, and we get triangles for boundary stabilizers and squares for bulk stabilizers. This is the whole set of stabilizers. We can still recognize smooth boundaries that are adjacent to green regions and rough boundaries that are adjacent to pink regions. The most economical codes have diagonally oriented boundaries like this. These codes achieves distance 3 with just 9 physical qubits and 8 stabilizer operators. Some of these stabilizer operators act on just 2 qubits. For example, sigma z1 times sigma z2, or sigma x3 times sigma x4. That was the present day. In the future, we want to compute with logical qubits. The standard scheme of computation includes qubit initialization, measurement in the standard basis. We need to measure a logical qubit in the 0-1 basis. Those measurement outcomes may be processed on a classical computer, and then we decide what gate to do next. That is a decision point. The gates may be Clifford gates. They are easier to implement. However, the Clifford gates are not computationally universal. So we also need so-called magic ancillars, special states prepared in a physical qubit. We first prepare an ancilla in a physical qubit, and it is initially unprotected from errors. But then we encode that ancilla or multiple ancillas in code blocks. An important part of the scheme is the implementation of Clifford unitary gates. We need to implement at least CNOT and the Hadamard gate, and they can be done transversally. CNOT is purely transversal, and the Hadamard is semi-transversal. It involves a 90-degree rotation of the code block. This is good in theory. In practice, it's inconvenient because the qubits are in the plane, and to do a rotation or a transversal CNOT, we have to move the qubits long distances. So the most efficient way compatible with the planar array architecture is lattice surgery. Lattice surgery was introduced in this paper of 4 authors. Austin Fowler is currently a member of Google Quantum team. The abstract idea is simple. Instead of CNOT, one can do XX and ZZ measurements. They're computationally equivalent to CNOT. Now, we do those measurements by surgery, that is, by cutting and stitching surface code blocks. This is one of the many beautiful pictures in the paper. The magenta qubits are used for stitching, and the Hadamard gate is implemented in a more complex way, but using similar ideas. Let me focus on the stitching. It's easier to describe the stitching using diagonally oriented code blocks where the extra qubits are not necessary. This is one block, and that is another block next to it. We replace those small stabilizers at the boundary with full plaquette stabilizers. And as we do so and measure the stabilizers, we may find some errors, so to speak. These are not actual errors. We'll just find a non-zero syndrome, which shows as a set of vortices at those dots. Vortices appear or do not appear randomly, but the total number of vortices modulo 2 indicates the XX eigenvalue of the initial quantum state on the two logical qubits. This is one scheme that will hopefully be implemented at some time. There is another scheme. This idea takes measurement-based computation to extreme. Instead of the logical Hadamard gate, we can do logical XZ measurements. The implementation is based on so-called topological twist defects. The picture shows two such defects depicted in yellow. These yellow pentagons are the defects. The defects are rather drastic, but there is also a line where the green-pink periodicity is broken and the corresponding plaquette operators are mixed. They have a mixture of sigma x and sigma z. When we cross such a line, when a charge crosses such a line, it becomes a vortex. A vortex crossing this line becomes a charge. And if we run a particle around such a defect, a charge becomes a vortex, and a combination of a charge and a vortex, a so-called E-particle, may just dissipate the defect. Each defect encodes half a qubit, or 1 Majorana mode. In this architecture, one can measure any Pauli operator or any even subset of Majorana modes at once by changing the stabilizer set. I'm not sure which scheme is more efficient, this defect-based scheme or the original lattice surgery scheme, but one of them or something along those lines will be implemented and will compute with logical qubits eventually. So stay tuned and thank you for your attention.